if you were looking for that other session, then you have moved to room C.1. Okay. So this is what we are going to do. The talk will consist of two parts. In the first part, we want to understand the basics of orbital mechanics, like the special phenomena which arise here. My goal is to give you some kind of intuition for this rather unintuitive topic. And then after we have mastered the basics of orbital mechanics, we are going to talk about this one weird trick from K theory. And I'm very sorry, and I'm actually not sorry at all for the Big Bang. Remember, this is a mathematics talk, so you have some responsibility that it will be a good talk. Please always feel free. You are very much encouraged to ask questions. You earn bonus points if you interrupt me as hard as possible in the middle of a sentence. Also, I have a remark.
Like now?
Also, I know that quite a few experts in orbital mechanics are sitting in this room. Please also don't hesitate to add further remarks and say things which I've forgotten. Yeah? Just let's do this thing together. We'll start with first of all a crash course in orbital mechanics.
Isn't the goal not to crash?
The goal is not to crash, right? Okay. So many people, when they imagine space, then they imagine it like Randall Munro has drawn it here on the right. They imagine space to be like far away. Like you have to go to the top, and then you have to continue and going upwards and upwards, and only after like millions of billions of kilometers you will reach the stars. Okay. I know how this imagination can come from, but it's actually not correct at all. So if you look on Wikipedia to check out what the definition of space is, then you will see that the consensus is that space begins at 100 kilometers above ground. 100 kilometers. So right now, I'm nearer to space than to my hometown. And in fact, it's not so hard to get to space. For this, you do not need like $1 billion. You do need a rocket, but it doesn't have to be as expensive. It can be a small little rocket. In fact, even with balloons, you can reach heights of like 30 kilometers, or 40, or 50, or maybe 60. Yeah? And then you just have to go like 40 kilometers more. I mean, what's 40 kilometers? That's a small distance, right? You could walk 500 before 40 kilometers. Okay. The problem is, so if you take a ball, for instance, and you throw it upwards, like very, very fast, yeah, then it will rise and rise and rise, and then eventually reach 100 kilometers, and then it will fall down again. Because gravity in a height of 100 kilometers is still approximately the same as on the ground. On the ground, we have an acceleration of 9.8 meters per square second. I think the square is missing there. And on the height of the International Space Station, you still have an acceleration of 8.7 meters per square second. It's almost the same amount. So of course, you've all seen videos of people chilling inside the International Space Station, and they're like freely floating. They are weightless. And therefore one could conceivably think that in space, like above 100 kilometers, there's no gravitation anymore. But that's not true at all. Yeah? The reason why it looks like and why it feels like to the astronauts that they are freely in space floating around is because they are at all times falling downwards to the Earth. And the ISS, the vehicle there inside is falling just with the exact same velocity. Therefore, you just see it appears as weightlessness, but in fact the gravitation of the Earth is still very, very, very strong. If you actually want to get to space and stay there, you have to increase your horizontal velocity. First, you have to get to 100 kilometers, and then you have to try really hard to accelerate in the horizontal direction in order to get so fast that you miss the Earth when falling. Wikipedia has a very nice illustration of this. Looks like this. So assume that you're on Earth and you're going inside some tower, and then you drop a rock. Yeah? If you just drop it, it will like do some parabolic flight, and then it will go down like 3 meters away from the point you started. If you push it like harder, yeah, then maybe it will go 10 meters or even 20 meters before reaching the ground. Okay, and if you throw it like really, really hard with a velocity of 11 kilometers per second, which is 40,000 kilometers per hour, which is like 40 times as fast as an usual airplane is going, assuming that the atmosphere wouldn't break, would stop the throw, then you would have this trajectory. The ball would go on and go on. It will always be falling, but also it will go in this direction, and it will always miss Earth. So by throwing a ball like really, really, really hard in the horizontal direction, you can make it go on a circular orbit around Earth. That's how you reach space and stay. You have to have a really high horizontal velocity. If you push the ball even harder, then you will increase the maximum height above the Earth. So your orbit will turn into an elliptic shape. If you throw it even harder still, the eccentricity of the orbit will increase even more, yeah, so that you have here more distance. And at some point, you throw it hard enough, and then you will have a velocity so that it never returns to Earth. This is part E. Okay. And I'm sorry, I just mixed up the velocities. If you want this part, then you only need 8 kilometers per second. If you want this part, you need 11 kilometers per second. Yes?
Did we imagine that the Earth will be only gravity in the universe? Also the trajectory will come back, right?
No, and that's a very good first question. Thank you very much. Even if you imagine the universe to be only consisting of Earth and no body whatsoever, then if you manage to achieve these 11 kilometers per second, and assuming there's no friction from the atmosphere, else you have to throw it harder, this is a trajectory which will never return to Earth. It will go on and on and on and on, and it will never return to Earth. This is called a hyperbolic orbit.
Actually, they are not round like a circle, but elliptic.
Yeah, well, there is a special case where it's circular. Like the first time you've managed to throw it so hard that it does not come back to Earth, then it will be perfectly circular. And if you throw it a little bit harder, then it will be elliptical. And if you throw it harder even still, then it will be hyperbolical. So that means it will leave Earth and never turn back. Yeah. Because you have not yet reached the necessary velocity for escaping Earth. There was a question in the back, I think, or somewhere.
Can you please repeat the questions from the first row so that
Yeah,
we can...
I will try to remember.
Thank you.
Correct. And if I don't, please just interrupt me. Thanks. I have a short table for you, namely the escape velocities you need for fully escaping the body in question, which is like going on the path E, leaving it forever, for all times. So for Earth, it's 11 kilometers per second. For Moon, it's much less. It's only 2 kilometers per second. This is because Moon has much less mass and therefore less gravity. If you were an inhabitant of the Sun and you wanted to leave the Sun, for instance, because it's so hot there, then you would need 620 kilometers per second. And if you decided that Milky Way is not a nice galaxy at all, you need to have 550 kilometers per second.
Is this dependent on how far I'm away from the center of gravity?
Yeah, this is very much dependent on how far away you are from the center of gravity. So this also explains why this is, in comparison to the Sun, not a ridiculously large number. You would think that to escape Milky Way, you would need like billions of kilometers per second. But that's not true. In fact, a smaller velocity suffices as for escaping the Sun. This is because we are very far away from the center of the galaxy. And there the gravitational pull of the center is less effective for us.
So where do we start when it's escaping from the Milky Way?
Like here in our region. Yeah.
So all the first three numbers are from the surface of the body,
Right.
and the first number is from where we are in the galaxy, not from the center of the
Right,
galaxy.
right, of course, yeah.
It wouldn't matter much if you're in the center of the galaxy as well, because most of the mass of the Milky Way is not much in the center. It's not a big black hole in the center, makes 90% of the gravity.
Yeah.
So there's a gravitational pull from the stars that are on the outside from your perspective too.
It does matter, because if you're inside the center of black hole,
You won't be
Very,
able
very one area. Right. Yeah,
So, do you happen
yeah, thanks. Yeah.
do you happen to know what gravitational pull the Earth has at the height of the Moon?
No, I don't know it offhand, but maybe one of the experts knows. And I repeat the question, thank you very much. What's the gravitational pull of the Earth, not at the height of the surface or at the height of the infinite space station, but at the height of the Moon? Does it know? Anybody?
Because the distance from Moon to Earth, 1.5.
It's one light second. So 300,000 kilometers. And you were going to calculate. Great.
380,000.
It's the speed of the Moon because the Moon space. Yeah.
We escaped the sun.
Yeah.
So between the first and the second phase velocity of
Yeah.
the sun. So
Yeah.
the situation is symmetric. So like falling into the sun
Yeah.
is also very, very hard for us.
Right. This is a very good point. I will repeat it. So often you hear proposals like, all this nuclear waste, we should just dump it into the sun. So at first sight, this is a good idea because in the sun, it cannot do any harm. The sun is like a nuclear ball. It's on itself, yeah, it's no problem. But reaching the sun is actually quite difficult. For this, you need like, it's symmetric. You need like this ridiculous amount of kilometers per second. So it depends on your definition what you want to do. Do you want to turn it to on orbit around the sun or to land on the sun? Decaying orbit would probably be not right.
But you need to reduce your speed because the Earth is rotating around the sun
Yeah.
at a very fast pace.
Yeah, and I show that in a
all
second.
that energy
Yeah.
in the reverse direction. So
Yeah.
therefore it is harder actually to reach the
Yeah.
sun than to reach Mars.
Yeah.
But that's the speed at the surface of the sun, and all we would need to do is just compensate the speed of the Earth, which is much lower.
And it's still a lot of
Yeah, it's awesome. It's not the 600.
Yeah, okay, it's not less than, but it's a lot. We can't play exactly these points in that minutes.
design the sufficiently reliable boosters.
Yeah.
Because we have plenty of nuclear waste around, and the launch abort sequence normally ends in a rapid unscheduled
Right.
service assembly.
Yeah, right. That's not a good idea. Okay, one more question and then we'll continue for now.
If you escape the sun at 600 kilometers per second,
Yeah.
can you escape the Milky Way at the same time? Because
Yeah, if you do it like cleverly in a clever path, you can do it.
If you
Yeah.
meet the question.
Yeah. If you try to escape the sun using these 600 kilometers per second, can you also manage to, in the same maneuver, escape the galaxy? The answer is yes. You can do it.
You lose velocity if you leave planet or not?
Yeah, the planet tries to hold you back. Yeah. But you may still have like velocity remaining. I think I want to continue with the next point, yeah. But maybe you will just, okay. I think I'll just do it, okay? Good. The second point is velocity is very important. So in ordinary life, it only matters where you are. So like when your friend is calling you, he's asking you, hey, where are you? Yeah, because he wants to reach you. In space, it would be much more appropriate to say, hey, where are you? And how fast are you traveling at the present moment? Because there's a huge difference, we've already seen it before, between being like 100 kilometers above the ground and having no horizontal velocity, because then you will just drop down again, or being there having a large horizontal velocity so that you encircle Earth. In ordinary life, you can always easily change your velocity. For instance, if you want to come to a full stop, then just wait a little bit for friction to pull you down. If you want to accelerate a little bit, then go faster on your bike. Yeah? But in space, changing velocity is always a difficult matter, and stopping is just as hard as speeding up. So when the Americans landed on the moon, they used like $1 billion to get off from Earth, and they used like $1 billion to stop when having reached the moon. Yeah? And remember, a couple months ago, there was this mission to Pluto, and it took pictures, but only for a very short time. And people asked, why did this mission not stay at Pluto and circle it for a longer amount of time? It was not possible because you would have to brake there, and it's like very, very hard to do. Yeah?
So if you need 618 kilometers per second of velocity to escape the sun, how did Voyager 1 and 2 do it?
I don't know it offhand. Probably because they use clever tricks, not unlike those we're going to see in part 2. It's a very good question, of course. It's a very good question. Yeah? Always double check what I'm saying. Really, I'm not an audit expert on this topic. I'm just a huge fan of the second part of this topic. One final remark. In the one-body problem, by this we mean the problem where you assume that there's only one body who is exerting gravitational pull, like only the Earth in the universe or only the Sun in the universe. There are exactly 3 kinds of shapes you can be traveling at if you do not start your thrusters and change the way you're traveling. Either you are on an elliptic orbit, perpetually revolving around the central body, or you are on a hyperbolic orbit, where you escape the body, or you are at a parabolic orbit. There's exactly one kind of it. It too looks approximately the same as a hyperbolic orbit. There you too escape the central body forever. The only difference between the parabolic case and the hyperbolic case is that at the parabolic case, you are getting slower and slower and slower. You still manage to escape the central body, but as the farther you go away from it, the slower you are. With a and eventually, like in infinite time, you will reach 0 kilometers per hour. But with a hyperbolic orbit, you still have some velocity left over. There was a question?
I think I have his answer, and I think it's what you just said. There were insertions at major objects, Saturn and Jupiter and other objects. That's how...
Like gravitational assists.
Yeah, through insertions at large objects.
Okay. Yeah, thank you.
Jupiter and Neptune.
I don't know offhand the trajectory of the body, but I should probably. Like, you know those nerds who are learning digits of pi to show off? They should rather learn the space path of a very important space. I didn't mean it in a derogatory way, by the way. I'm one of those nerds who learned it quite time.
What was the question?
500. A final remark on this slide, then we'll continue. Always remember to keep your model straight. Oftentimes we will be neglecting the atmosphere. And a very important point is to really not neglect is to check whether you need the Earth to be rotating around itself for your arguments to make sense or not. For instance, a space elevator will not work at all if the Earth didn't rotate around itself. Then you would just go 100 kilometers to the top, yeah? And if you were to drop an apple there, it will just fall back again because, as we've discussed, the gravitation is almost exactly the same as on the ground. Okay, now it's time for some light demo for changing orbits. So let's hope that this works. Okay, so in the middle you see Earth, it's blue, and here you see ISS, International Space Station, and here you see a rocket which is trying to carry like persons or cargo to the ISS. And you see by this initial conditions, it's always it's already on the right orbit, but it's just like the angle is not correct. Yeah, it has to speed up a little bit. So let's try this for this body to catch up with this one. I can click here and then I can apply acceleration in any direction I want to. And at the top upper right, I will see the amount of change in velocity. I do that. You will now try to tell me what to do, and it's a rhetorical question. Yeah? So I'll answer it myself. Imagine you are on the highway, yeah? And you're traveling with 100 kilometers per hour, and this guy in front of you is traveling, and you want to catch up on him. Yeah? Then what you do, you simply accelerate a little bit, then you will go faster, and eventually you will meet up with him. This is a very basic strategy. It works in real life. That's the idea. So let's move a little bit into the direction of the ISS.
Damn it.
This didn't work at all.
So the main thing is that although Kepler is your friend and the faster the faster
Whoa!
like the relationship of the two, those are still irrational numbers, so it's pretty unlikely that you somehow like, catch up.
Yeah, and even at some moments, like you were cheering, when they were in the very vicinity of each other, they still had a huge difference in velocity, right? So it's like very hard to catch up on those.
Especially if you got like
you could have decelerated exactly to the same speed.
Yeah, that you could have probably done, yeah. In fact, the first attempt in space to dock two things together failed because of precisely this reason. There was a question or a remark? Yeah.
The way you do it is you slow down and lower your periapsis to become lower. Then when you reach the axis, you lower your apoapsis, so you're in a lower orbit.
Right.
And then when the ISS is at the right phase angle,
yeah.
you're high in your apoapsis again for an orbit.
Yeah, exactly. You earn a third point. Are very valuable and they are very, 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 very good.
Then when you reach there, you raise your periapsis.
Right. So we'll brake. Yeah. Do you see the arrow? The direction of the arrow. We'll brake now. Okay. This way, we are getting faster inside of it. Yeah. And by chance, so this, let's try to do it again because we didn't have the right velocity. Yeah. Brake, and at some point I just have one attempt, and I don't care whether I fail or not. Like this, speed up again. Yeah. This is how you do it. Quite nice, namely about the new orbit. You always know at least one thing, namely it passes through the point where you did the acceleration. This is always true. Yeah, we can do it again. Like, wait a little bit, and I'll do it here. Yeah, let's keep this point in mind. There. Do some acceleration. I hope I'm not leaving this also. No, no. And then here, I will be still there. Yeah. If I do some maneuver, and the maneuver is not so hard as to leave the planet forever, then I will be on an elliptic orbit, and it will return to this point in space.
But it assumes that the acceleration is near instantaneous.
Right, yeah. In this demo, I'm assuming that the acceleration is always done like in a nanosecond, whereas in fact it can go over seconds, minutes, hours, or even days.
By a kilometer per second in a nanosecond.
Yeah.
Maybe we have to worry about those astronauts anymore.
Right. Okay.
What would happen if you accelerated towards Earth?
A very good question. I spent many hours yesterday to. The question is, what happens if you accelerate towards Earth? Let's just try it. So here, for instance, and we want to accelerate towards Earth. So in this direction, yeah. Okay. This happens. So it's weird. If you want to think about this, I encourage you to do two things. First of all, after the talk, come to the front and ask questions to this smart guy. Great fan of you. Second, do it here. And always keep an important distinction for this in mind. It's what he just said. For this situation where you try to accelerate towards your body, that actually makes a slight difference whether you do it over a whole amount of time, like 10 minutes, or whether you do it instantaneously. As you will see, slightly different effects. Yeah.
So you should probably play Common Space.
Of course you should play Common Space program.
Of course.
That was good.
How do you think I know?
Yeah.
If you're on the ISS
yeah.
and you're like working outside and have this jetpack,
yeah.
if you want to go back to the ISS, so you actually have to fly away from it or like decelerate?
No, as long as you're like in the near vicinity of the ISS, this weirdness of orbital mechanics does not come into play, and you can just get as normal. I mean, you don't have friction, so you have to be a little bit careful, do not like overshoot and so on. But other than that, you don't have to keep track of anything. But as soon as you're like 2 kilometers away, you have to pay careful attention to orbital mechanics.
How much? 2 kilometers?
Approximately 2 kilometers.
Okay.
Yeah.
Especially if you have basically no delta V in the backpack.
Right, yeah. I think I should talk about the word delta V just for a second before we come to the second part of the talk. So in ordinary life, you measure the usage of how much fuel you need, like in liters, yeah? You need so many liters of gasoline to reach your target. The unit in space travel is instead delta V, the change in velocity required. For instance, to leave Earth, you need a delta V of 11 kilometers per second. You need to have a rocket which is so good in order to exert 11 kilometers per second. And for those maneuvers, you see here at the top, this maneuver needed 0.3 kilometers per second. Yeah, and if you just, for instance, if you need to do 5 maneuvers, then you can just think about what delta V you need at each of those points where you're doing the maneuvers. Then you can add those individual numbers, and this is your delta V budget. This is how much fuel, this we can translate into fuel, and this is how much fuel you have to carry in order to do that. The international measure for hardness for reaching things in space is delta V. Okay, yeah?
Branko, what's the basic kilometers per hour that everyone kind of understands that you can give what a kilometer per second is? In other words, I'm asking him, or you, to give us what I would call the natural speeds we're used to. Is it 100 kilometers an hour? Is it 0.001 second?
You want 1 kilometer per second translated into kilometers per hour?
Yeah, just a rough translation for it.
Yeah, it's what?
Factor of 3.6.
Factor of 3.6 in what direction?
1 meter per second equals 3.6 kilometers an hour.
Okay, so this is 3,600 kilometers per hour if you are in the kilometers per second range. Yeah. Okay. Let's talk about a topic which is not very pleasant, namely the tyranny of the rocket question. Rocket scientists hate this. Sorry?
I'm just cursing that guy.
Ah, right. So, how do you change velocities in space? So the cool new thing is to do like ion drives and so on, but the conventional way to doing is to exhausting gas in the direction where you do not want to go. Yeah? So you're like putting gas into this direction, and then by the law of conservation of impulse, you will be traveling that way. Okay? This is how you change the velocity, how you accelerate and brake in space. But fuel itself has a mass. Fuel takes space and it has a mass. So if we have some payload, like for instance some astronauts or some scientific instruments which you want to get to space, to orbit, to moon, whatever, you need some fuel for the payload. But then the fuel itself has mass. Therefore, the total weight of your rocket just increased. You need some further fuel in order to be able to lift up the fuel you just had put in. Now, your rocket just got a little bit heavier again. You need even more fuel to lift this, and so on and so on. So the good message is that this is not a vicious circle. This is not an infinite circle. It's not the case that you would need infinite fuel to reach moon. But it's an exponential circle. You need the total amount, the total mass of your rocket will be the mass of your payload, which what you're actually interested in reaching space, times the exponential function in delta V. And you know the exponential function is like increasing very fast. And this is why rocket scientists are so like fixated about this delta V. If by some circumstances you could manage to reduce the delta V needed by just a tiny amount, like a couple %, because rocket scientists would be extremely happy, because a small reduction in delta V yields a large reduction in the total amount of fuel you will need. Conversely, if you need a little bit more of delta V, then you have to add in lots of more fuel. Yeah? And these new ways of reaching space and doing things we will talk about in a second, they have little delta V savings, like 10%, 20%, 30%, but it's completely changing the board because of this exponential dependence. Yeah?
And the rocket is made out of fuel and fuel and fuel and a little bit metal.
Yeah. It's just fuel. It's a sad thing. This is because this is also why people are like very excited about alternative methods where you do not have to carry your fuel with you. For instance, you have a nuclear reactor on board on the spacecraft, which just generates energy. Yeah. Yeah.
Is it called the natural logarithm?
So normally this equation is solved for delta V, and then you will have the natural logarithm appearing there. But I wanted to give the formula for the total mass, and then it's the exponential function. Later on, I will give you a present, namely a little card for keeping in your pocket about the exponential function. They will have like 500 digits of the each of the one. And there was a question?
What's the achievable ratio of fuel to dry plate of the spacecraft?
I don't know. Okay, let's come to the second part of the talk. Okay, one clear trick from chaos theory. So what's chaos theory? Chaos theory, you've probably seen Jurassic Park, where it was very neatly explained. Chaos is when things depend very, very sensitively on the initial conditions. Yeah? For instance, I have this book, and if I drop it, it drops. And if I were to drop it a little bit with a slight direction, it will drop just to about the same pace. This is not a chaotic system. Okay? But if I have a pen, and I would balance the pen on my finger, it would be a chaotic system. So at first, it would like stay upright if there were no gas molecules hitting it. But then, yeah, it depends very, very sensitively on all the matter in the universe. This pen is like really, really intelligent. It detects all the matter in the universe and all the gas molecules hitting it, and then it decides to go for any of the possible directions. This is a chaotic system. The standard example, thank you very much, is like the wings of a butterfly can cause gigantic storms. Therefore, the tiny effects add up and add up and up, add up, and suddenly you have a giant storm. This is what can happen with chaos. So this seems like to have to be dangerous to exploit, but actually it's what these people are doing. Yeah.
Are quantum effects respected in a chaotic system, or are they just left aside because they are unpredictable?
For these kind of lines, we do not need any quantum mechanics, but we do need the general theory of relativity, yeah, to have the orbits exactly right.
General or
I think at some points you actually need the general theory, which is like
For you accelerating.
Yeah.
A purely accelerating frame of reference is still special.
What's the problem about conventional space travel? The problem is you need so much fuel to do things. That's the first problem. You need $1 billion to get off from the Earth, $1 billion to stop at the moon. This has more serious, so even if money was of no importance, this would still be a problem. Because at these space missions, you need to ensure that your rockets are able to fire again after they've been in space for maybe quite a long amount of time. Yeah? You're sitting like on this gigantic ball which can explode at any second. Yeah? You have to make sure that it does not explode at all in the several months you are taking to, for instance, travel to the Mars. And then you have to ensure that they go up again in exactly in a controlled manner to do exactly those maneuvers you want to do. With these new tricks, you can do the following. You start at low Earth orbit. You do one very special kind of maneuver for which you need fuel. And then you switch off your engines and you will never need them again. The spacecraft will travel by itself on a very complicatedly shaped orbit trajectory to your destination. It might take several rounds to do this. And then at the destination, it will almost by itself, it will only need a very, very tiny touch. It will not need huge rocket engines. It will just need a tiny touch to land on or to get into an orbit around the body you will be studying. You do not need to brake with this approach. Yeah? You start Earth with lots of fuel, and then the rest of the trajectory is happening on itself, and the braking at the target is also happening by itself. And I want to explain to you how this is possible. Yeah, very short.
Just have a slight request. A lot of people are talking behind us.
Yeah.
They're not really respecting the fact that you're talking to something that's really interesting. They think that their talks are more interesting than yours. So I would ask everyone to please focus on this.
Yeah, okay.
Fair enough.
Yeah. Okay. The first thing to notice is beforehand we always thought about a central body in the center. And there are situations where intuitive, but easy after you have mastered them. There were three types of trajectories: elliptic orbits, parabolic orbits, and hyperbolic orbits. The situation is completely different with a larger system consisting of many bodies which each have a mass which you cannot neglect. Like for instance Earth and Moon, or Earth, Moon and Sun. I'll show you an example. Here. So now we have the Earth in the center, the Moon at the top, and some rocket. And I just want you to watch that this is not the kind of orbit you've known like from the first part of the talk. Because your thesis. So at the end, this was a numerical error, yeah? Because there are very fancy algorithms for doing this right, and there are also very naive ones. And I picked the third most naive one imaginable. But you've seen this, yeah? Like these spontaneous size changes here, these do not happen in a normal one-for body problem. So in fact, there's no characterization of how the path could look like in a multi-body system. They are not restricted to ellipses and hyperbolic orbits and so on. They can look very weird, very chaotic. They can make like any motion imaginable. Yeah. That's the first thing to keep in mind. The trajectories are much, much, much more complicated. Okay. I want to tell you about the Lagrange points, Lagrangian points. Okay. You have the Earth, and you have the Moon. Earth, and you have the Moon. Okay. Between those, so you have the Earth and the Moon. And now we'll switch the reference system we are considering. We are no longer like looking at it from the top, yeah, on the top of the solar system, but we'll move as the moon moves. Okay. I'll now make a demonstration of what the movement of Earth and Moon looks like if we move along the axis they was traveling. It looks like this. Okay? So in reality, Moon is traveling, but we are moving our eyes, yeah, with the Moon. And then it just looks like this. Okay? I'm only changing the reference systems. It makes things easier for what I want to do. Okay. Now there's a special point between the Earth and the Moon called the first Lagrange point here. And it has a very special property, namely, if you put something there without velocity, it will just stay there forever, your first approximation. At this point, all the forces cancel each other. At this point, you have a force, gravitational force pulling you to the Moon. You have a force pulling you to the Earth. And you have a centrifugal force pulling you outwards. The centrifugal force is what you experience if you do with a partner like this thing, yeah? Then both of you are experiencing a force outside of the common center. And at this Lagrange point, L1, all those forces exactly cancel. We have a demonstration of this.
What's the reference point with this example?
What do you mean by...
the example where you said the moon is like that and it doesn't move. We are seeing from the point of view.
Imagine a line between the moon.
Yeah, imagine a line between the Earth and the Moon. And yeah, then L, Moon, and L1 is this green dot here. And so the simulation is already running. I have not pressed pause. It's already running.
Isn't there a fifth point?
There's a fifth point. There. Right. These are the 5 Lagrangian points. These are the points where all the forces involved exactly cancel. I want to explain first for a second point, just to have an idea for this one. This point experiences gravitational pull to the Earth, to the Moon, and outwards of the common point of center where Earth and Moon revolve around, which is like slightly to the top of the Earth, like here. It's 4,000 kilometers from the center of the Earth. Yeah? So people always say that the Moon is revolving around the Earth, but that's not quite true. In fact, they're revolving around each other. Yeah? Before I take the question, just let me show this to you, because they don't show you this in school. Like, just have a look. Don't look at the ISS, just look at Earth and Moon, yeah? You see the Earth wobbling. This is because Earth and Moon rotate about the common center of mass. Yes? Okay. And you see this weird chord shape.
That's why there's twice a day of flood and the tide coming.
Yeah. Okay. So, questions? Yes?
That was a nice example of Bayes' theory, because the first time you had the numerical error.
Yeah.
The second thing is actually a question.
Yeah.
The Lagrange points already sound unstable.
Yeah. Right. This is a very good point. I'm sorry, I'm going to skip this question because I want to show you cool things and they're only like 0 minutes. Give me now. Yeah. So first, I speed up the simulation. Yeah.
Numerics again.
Oh.
Damn.
Can you show us the numbers you're changing?
The speed up factor.
I thought there were numbers up in the upper.
No. I didn't make any maneuvers.
Oh.
I just sped up the simulation. And then you see an interesting thing. So by numerical errors, like I do a rounding error each step I'm calculating the new frame, right? Okay. So by numerical errors, those bodies placed at those Lagrangian points slightly moved away from the Lagrangian points. what are the consequences? So if you have this L1 point, yeah, I'll restart the simulation. Yeah. Here, this point, L1, yeah, assume that it was slightly off, for instance, slightly near to the Earth. Then the pull to the Earth will dominate, and it will start falling towards the Earth. You can see it? See it? It scrolls towards the Earth. And it's also deflected because of centrifugal force and Coriolis force. Yeah? And then it does crazy stuff. The same is true here because of numerical rounding errors. The body slightly leaves the Lagrangian point, but as you were able to observe, okay, I was too impatient. I accelerated too much, and then the numerical errors controlled everything. This is a good speed. These two Lagrangian points, L4 and L5, they are called stable. Because if you slightly deviate from those points, you will not go into crazy things, but you will stay around those points forever in a chaotic fashion, but you will stay around those points. I think this is quite cool because normally, so you're accustomed that things rotate around like a central massive body. Yeah? The moon is rotating around the Earth. Okay. You're not accustomed for things to travel around some imaginary point in space where nothing is there. Yeah? And the Lagrangian point is just a mathematical thing. There's no like sun or planet there. And still, bodies can orbit that imaginary point. Okay, and now let me try to explain to you what's the idea of these new kinds of interpretabilities are. Okay. So you've seen these Lagrange points. These Lagrange points are very extremely sensitive on the initial conditions. If I'm at one of the Lagrange points and do just a slight touch in some direction, just very much, just a little bit, yeah, then you can exert great consequences later on. Okay. And now it turns out, this work by pioneering work by Belbruno in the 80s, that there are things called weak stability boundaries. So here you see the moon, and then you see several layers drawn around it, approximately spheres, but like very distorted spheres. Yeah? One for each velocity. If you manage to arrive at such a point with the correct velocity, then a very special thing happens. Namely, you enter a chaotic motion which for some time stays on this weak stability boundary. Yeah? If you manage to arrive here and have the velocity as indicated by the arrow, you will go like in a crazy fashion, but you will stay on this weak stability surface, weak stability boundary. If you now do a little touch to the inside, you will be captured by the planet. You will enter a stable orbit around the planet. By contrast, if you do a slight nudge away from the central body, you will leave the system. You're exploiting the chaotic dependency of the great sensitivity on the initial conditions. If you just chill and do nothing, yeah, then you will have a chaotic motion for some point, for some amount of time, and then you will randomly either get attracted to the central body or you will get pushed.
How much is a slight touch?
Slight touch means you can do it with Manövriertriebwerke, like maneuvering thrusters, like very, very small amounts of delta V.
But not like molecules or something?
No, not molecules, but...
it depends on their speed.
It depends on the speed.
This is one body problem, or...
No, this is not the one body problem. So with the one body problem, where you assume that there's only one body having gravitational effects on all the others, you do not have any kind of chaoticity. You don't have any kind of chaos. You only have these chaotic effects if you consider 2 or 3 or even more bodies, each having gravitational effects on all on themselves and also on the rocket. Yeah. So how do you use these kind of weak stability boundaries? For instance, you want to reach the moon, yeah? And you want to do it without braking at the moon. You want to do it ballistically. You want the moon to capture you. Yeah? Then you pick some point on this velocity, on this boundary, yeah? And then you calculate backwards in time where you would have, then you find a point where you need to start so that in the future you arrive there. And when you arrive there, and you just have to do a little touch, and you will be captured by the moon.
By the way,
yeah.
You said towards or away from the moon.
Yeah.
Are you really talking about?
No, I'm not talking about radio, but I'm talking about asking him and then like finding the record.
The dot in the middle, is that indicating the moon?
Yeah. No, the moon. Okay. So this before was a graphical sketch. This is an actual plot from a scientific paper. Like you see the boundary like here. Yeah? And these are the orbits around the stable Lagrange points. Just want to show you that it's not like an idea of it. Yeah? And in fact, I want to tell you one last story in 2 minutes. The rescue of the, sorry, no time questions. The rescue of the Haiti. So this was the first lunar probe by the Japanese, and they were like very happy. It was a satellite containing a smaller satellite, and the goal was for the smaller satellite to reach moon. The larger satellite was never meant to go to moon. It didn't have enough fuel. It only was there to keep the smaller satellite into orbit and then give it a push to the right direction. Okay. So the problem was, after the small satellite separated, contact was lost, and we do not know to this point what's ever happened to the small satellite, which was this time to go to the moon. So the Japanese were left with a functioning satellite in orbit of the Earth, but which did not have enough fuel to reach moon. Remember, $1 billion, and then again $1 billion. Bell Bruno, the mathematician who worked on this paper, noticed it and wrote a fax to the Japanese Space Agency. And by some kind of miracle, it was actually noticed by some nerd working there and was not got into crash. And then Bell Bruno devised this orbit, this trajectory for the Heaton to reach moon. And the Japanese guys tried it, and it worked. It was like this. Here at the end, you see the weak stability thing. You have to reach it. For this, you have to creep on very, very slowly to it. And the way he did this was first go to a point which is far away, point C. There you have chaos. You have very sensitive conditions on the initial things. Yeah? With a slight change there, you can achieve great consequences later on. In this example, the great consequence later on was that it turned backwards to reach the weak stability point. And there, the Heaton probe only had to do a little touch in order to be captured by the moon. And I want to tell you the problem with this approach. The good thing is you need vastly less delta V, and you do not have to carry like high-powered rocket fuel till the end of your journey, yeah, where all things can go wrong, where it can explode, where you may fail to start it again. The bad thing is it takes more time. The usual travel time to the moon is like 3 days. This year took 2 years. Yeah? It took like 1 year to go from the orbit it was previously on to this orbit, and then 6 months from here to here, and then a further 6 months to change it to the correct orbit they wanted to have around the moon. My final picture, and then enjoy the other sessions. This is all two happening in nature. So here you see stars getting sucked away from some galaxy via some kind of this low energy trajectory. Yeah? This is called the Intergalactic Transport Network. And also there are like comets traveling on these kind of trajectories. Comets for like 80 years are traveling and this way going to destinations which they couldn't reach otherwise. And I think now it makes sense of this picture here at the beginning of part 2. This is the natural interplanetary transport network. It's the closest approximation we have to true wormholes. Thank you very much for your attention.